Welcome to the Explainer. Today, we're jumping right in and bridging the gap between abstract C++ concepts and exam-ready code implementation. I'm absolutely thrilled to guide you through this material because honestly, once you grasp these design patterns, your code is going to become infinitely more flexible and professional. Let's get to it.
Okay, looking at our agenda for today, we're covering pure virtual destructors, abstract classes and interfaces, operator overloading examples, generic programming fundamentals, generic classes and templates, and wrapping up with our core takeaways.
Section 1. Pure virtual destructors. Handling the undefined reference edge case.
So this is a notorious exam edge case that literally trips up students all the time. The absolutely crucial point here is that unlike normal pure virtual functions, a pure virtual destructor still absolutely needs an implemented body. You might be wondering why. Well, because when a derived class object is destroyed, its destructor automatically calls the base class destructor. If that base destructor has no body, the compiler gets incredibly confused and boom, you get a nasty linking error.
And looking right here on the screen, this brilliantly illustrates the exact code required to fix that issue. Take a look specifically at lines 7 through 10. Even though the destructor is declared as pure virtual up on line 5 with that equals 0 syntax, we still provide a function body right beneath it. It's a simple addition, but it completely prevents that dreaded undefined reference error when your program tries to clean up memory.
Now check out this terminal output. When a dynamic child object is deleted, you'll see the destructors fire in a very specific, very safe order. The derived class destructor executes first, cleaning up the child-specific memory, and then it's safely followed by our pure virtual base destructor. This sequence basically guarantees you won't have any memory leaking.
Moving on to Section 2, abstract classes and interfaces, defining behavioral blueprints.
Now, let's look at how we actually design higher-level blueprints. A classic assignment example you'll likely see is creating a generic shape base class. This acts as a foundation for specific geometry, right? Like triangles and rectangles. Obviously, you can't calculate the area of a generic shape, but you know for sure that every shape must have an area. And that is the core idea of an abstract class.
To build out this concrete class hierarchy, you need to follow these exact steps. So your base class holds the shared logic, like the get_data function. But the real magic happens when you make display_area a pure virtual function. By doing that, you're essentially forcing the derived concrete classes, the triangle and the rectangle, to redefine and implement that area calculation uniquely for their specific shapes.
Okay, notice the strict dividing line here between these two very common terms. An abstract class gives you partial implementation, meaning some standard functions mixed with at least one pure virtual function. An interface, on the other hand, it's purely a structural contract with absolutely zero implementation. Literally nothing but pure virtual functions and an empty virtual destructor.
Looking at this code snippet, my abstract class is a perfect example of an abstract class. It mixes standard, fully implemented methods, like method 3, with the pure virtual method 4. And it's the presence of that single equals 0 that makes the entire class abstract, meaning it's uninstantiatable. You just cannot create a direct object of this class.
Conversely, check out the interface pattern we have here. Every single method is pure virtual. There's no logic, no variables, just rules. And really importantly, it's accompanied by an empty virtual destructor to ensure proper memory cleanup for any class that decides to implement this interface.
Section 3. Operator overloading examples. Comparing custom objects.
Let's see how we give our custom objects some built-in functionality. If an exam asks you to compare two custom string objects, you can't just use a normal double equals sign right out of the box, right? You have to literally teach C++ how to compare them by overloading the equals operator. You do this by creating a function named operator equals equals. Inside there, you use the standard C library string compare function, string compare, to evaluate the underlying character arrays. Since string compare returns 0 when the strings match, you just catch that and return a 1 for true or a 0 for false.
And doing that results in incredibly clean, readable code. In your main function, you don't have to call clunky, awkward functions anymore. You can just use the standard double equals sign to compare two user-inputted strings. As you can see in the output here, it perfectly evaluates that our sweetest songs absolutely does not equal a burning desire.
All right, Section 4, Generic Programming Fundamentals, Escaping Data Type Limitations.
So far, we've only dealt with specific data types, but what if we want to write code that works universally? Well, to understand how we solve this, we kind of have to look at the paradigm shift across programming history. We moved from procedural C to object-oriented C++, which, by the way, introduced the absolute magic of generic programming. Later on, C++11 pushed us even further into functional paradigms. But generics, they are the bridge that completely changed how we write reusable code.
Generic programming is basically this big idea that your code should be completely independent of data types. So instead of writing a sorting algorithm for integers and then overloading it with another one for doubles, you just write one generic algorithm. The types, you specify those later. It's a total game changer that massively increases efficiency and cuts way down on code bloat.
Which leads us to Section 5, Generic Classes and Templates, Auto Code Generation.
Transitioning from all that theory to actual C++ syntax, templates are the real hero here. They work as a form of meta-programming. You write a template, and the compiler automatically generates the correct source code based on the specific data types you pass to it at runtime. It's essentially writing code that writes other code for you, and that is incredibly useful for universal data structures like stacks or queues.
Make sure to lock in this exact syntax for your assignments. You absolutely must prefix your class with template class T. That uppercase T is just a placeholder. It basically tells the compiler, hey, I don't know what data type this is going to be yet. Maybe an int, maybe a string, but wherever you see a T in this class, just swap it out for the real data type later.
And remember a few essential rules here. The actual data type is passed dynamically when you instantiate the object. Plus, you aren't limited to just one generic type either. You can totally use a comma-separated list, like class T, class U, if your class needs to handle multiple different unknown data types simultaneously. Oh, and you can comfortably mix generic variables with standard non-generic ones inside the exact same class.
Finally, Section 6, Core Takeaways and Recap, your study guide summary. Okay, we've covered a lot of dense academic ground today, so please keep these final programming patterns in mind. First, always provide that pure virtual destructor body to avoid those undefined references. Second, know the strict difference between an interface with zero implementation and an abstract class with partial implementation. Third, use operator overloading to compare custom objects natively. And finally, rely on templates to achieve generic programming and literally eliminate duplicate code.
So, as you head into your next lab assignment, I want you to ask yourself, how will you use generic programming to write cleaner, smarter, and infinitely more reusable code? Because mastering these concepts really shifts you from just writing C++ to actually engineering it. Thanks for joining me on this explainer, and happy coding.